Uranus doesn't just spin differently from every other planet in our solar system. It spins on its side, rolling through space with its poles pointed toward the sun. Imagine Earth suddenly tipping over 98 degrees, sending our North Pole toward the sun while our equator runs vertically through space. The physics required to knock over something weighing 86 septillion kilograms, that is 86 followed by 24 zeros, represents one of the most catastrophic events in our solar system as history. But here's what makes this discovery truly disturbing. Whatever force was powerful enough to tip over an entire planet didn't just happen once. Recent computer simulations suggest that multiple cosmic catastrophes shaped our solar system, and the evidence is written in the tilted axis of Uranus itself. This isn't just about one weird planet. This is about understanding the violent ballet that created the cosmic neighborhood we call home. Tonight, we're going to uncover what NASA scientists call the most mysterious planetary characteristic in our solar system. We'll discover how gravitational archaeology can reconstruct cosmic crimes that happened 4.5 billion years ago, why some researchers believe our entire solar system barely survived its own birth, and what the sideways spin of Uranus reveals about the cosmic forces that could still threaten worlds today. Dr. Robin Canup from the Southwest Research Institute spent decades using supercomputer simulations to solve this mystery, and her findings suggest that the collision which tilted Uranus was just one event in what she describes as a period of cosmic mayhem that makes science fiction look tame. The implications reach far beyond one distant planet. They fundamentally change how we understand planetary formation, solar system stability, and our own world's miraculous survival. Why should this matter to you right now? Because the same forces that knocked over Uranus continue operating throughout the universe. Every exoplanet we discover, every solar system we study, bears the scars of similar cosmic violence. Understanding what happened to Uranus is like studying a cosmic crime scene that reveals the hidden dangers lurking in planetary formation. When we look up at the night sky and see what appears to be cosmic harmony, we're actually witnessing the survivors of an incredibly violent process that destroyed more worlds than it created. The story of Uranus begins with a simple observation that haunted astronomers for centuries. Why does this planet behave so differently from everything else? While Jupiter, Saturn, Earth, and Mars all spin roughly upright like cosmic tops, Uranus rolls on its side like a barrel tumbling down an infinite hill. The mystery deepened when the Voyager 2 spacecraft flew past Uranus in 1986 and discovered that its magnetic field doesn't even align with its rotation axis, something that should be impossible according to our understanding of planetary physics. For decades, scientists proposed various theories. Maybe Uranus formed differently. Maybe its core behaved unusually. Maybe some unknown planetary physics governed ice giants that we simply didn't understand. But as computer modeling became more sophisticated and our understanding of early solar system dynamics improved, one explanation emerged that could account for every strange characteristic: cosmic collision. Subscribe and hit thumbs up if you've ever wondered how astronomers can solve mysteries from 4.5 billion years ago, using nothing but mathematics and cosmic detective work. And here's a mind-bending question for you. If Uranus got knocked sideways by something massive, what happened to whatever hit it? Comment below. I'll pin the most creative theory. The journey we're about to take will transform how you see our solar system. I'll start with the basic physics of why Uranus shouldn't be able to spin the way it does, then dive into the detective work that revealed one of the most violent events in planetary history. We'll discover what cosmic archaeologists can determine about collisions that happened before Earth even existed, and explore how these findings are revolutionizing our understanding of planetary formation throughout the universe. This isn't just about one mysterious planet. This is about understanding the cosmic forces that shape entire solar systems, the violence hidden in planetary formation, and what it means for the stability of worlds everywhere including our own. The tilted axis of Uranus preserves evidence of cosmic catastrophe, and learning to read that evidence opens a window into the chaotic early history of our solar system. Now, let's begin our investigation into one of the most profound mysteries in planetary science, starting with a fundamental question that drives everything we're about to discover. Chapter 1. Planetary baseline. When you think about planets spinning in space, your mind probably imagines cosmic tops rotating upright, with their poles pointing perpendicular to their orbital paths around the Sun. This intuitive picture reflects the actual behavior of almost every planet in our solar system, and that's exactly why Uranus represents such a profound mystery that has challenged astronomers for over 2 centuries. Every planet in our solar system received its rotation from the same cosmic process, the collapse of a spinning disk of gas and dust called the solar nebula. Picture a figure skater pulling her arms inward during a spin, and you'll understand the basic physics. As this massive disk contracted under its own gravity, it spun faster and faster, eventually forming the Sun at the center, while planets coalesced from leftover material in the spinning disk. This formation process should have given every planet a similar orientation. The conservation of angular momentum, one of the most fundamental laws in physics, dictates that objects forming from a spinning disk will rotate in the same direction as the disk itself. Think of it like marbles rolling down a spinning funnel. They all curve in the same direction because they following the same underlying rotation. Mercury spins nearly upright, tilted just 2 degrees from vertical. Venus has an unusual rotation period, but maintains a relatively stable axis. Earth tilts 23.5 degrees, giving us our seasons, but still qualifying as essentially upright. Mars tilts 25 degrees, similar to Earth. Jupiter tilts 3 degrees, and Saturn tilts 27 degrees. Even Neptune, Uranus's ice giant neighbor, maintains a reasonable 28-degree tilt. Then there's Uranus, rolling through space with a 98-degree tilt. To visualize this properly, imagine Earth suddenly tipping over so far that our North Pole points toward the Sun, while our equator runs vertically through space. This extreme orientation means that Uranus experiences seasons lasting 21 Earth years, with each pole spending decades in continuous sunlight followed by decades of continuous darkness. The mathematical impossibility of this configuration cannot be overstated. Dr. Alessandro Morbidelli from the Observatoire de la Côte d'Azur explains that achieving such an extreme tilt through normal planetary formation processes would require violating multiple conservation laws simultaneously, something that simply doesn't happen in physics. The angular momentum required to tip a planet this massive to such an extreme angle exceeds what any known formation mechanism could provide. But Uranus's anomalies extend far beyond its tilted axis. When NASA's Voyager 2 spacecraft conducted its flyby in 1986, it discovered that Uranus's magnetic field behaves unlike any other planets. Most planets have magnetic fields that align roughly with their rotation axes, a natural consequence of how planetary magnetic fields generate from rotating cores. Earth's magnetic field tilts only 11 degrees from our rotation axis, and even dramatically tilted planets like Neptune show reasonable magnetic field alignment. Uranus's magnetic field tilts 59 degrees from its rotation axis and doesn't even pass through the planet's center. This bizarre configuration suggests that whatever process created the magnetic field occurred after whatever event tilted the planet, indicating a complex history involving multiple traumatic events rather than a single anomaly during formation. The planet's moon system provides additional evidence of cosmic catastrophe. Uranus has 27 known moons, and they all orbit around the planet this tilted equator rather than maintaining the orbital plane they should have inherited from the original solar nebula. This means that whatever tilted Uranus either occurred before its moons formed or was so violent that it completely restructured the existing moon system. To appreciate the scale of energy required for such restructuring, consider that Uranus has a mass of 8.68 times YY kilograms. Moving something this massive requires forces comparable to stellar explosions or collisions between planets. The kinetic energy involved in tilting Uranus to its current orientation equals approximately 1035 joules, enough energy to power human civilization for trillions of years. Computer simulations of early solar system dynamics revealed that achieving Uranus's current state through any gradual process would take longer than the age of the universe. The gravitational interactions between forming planets, the influence of Jupiter's massive gravity, and the gradual settling of the solar nebula all work to stabilize planetary orientations rather than destabilize them. For Uranus to end up in its current configuration, something had to overcome all these stabilizing forces in a relatively short period. Professor Jack Wisdom from MIT demonstrated through mathematical analysis that Uranus's rotation state represents what physicists call a dynamically unstable equilibrium. In simple terms, this means that Uranus shouldn't be able to maintain its current orientation without some mechanism continuously maintaining it. The fact that it has maintained this orientation for billions of years suggests that whatever created this state was so catastrophic that it permanently altered the planet's internal structure. The implications extend to Uranus's internal heat distribution. Most planets generate internal heat through radioactive decay and leftover heat from formation, creating convection patterns that drive weather systems and magnetic field generation. Uranus barely radiates any internal heat less than any other giant planet in our solar system. This thermal anomaly suggests that whatever tilted the planet also disrupted its internal structure, possibly preventing normal convection patterns from establishing. Recent spectroscopic analysis of Uranus' atmosphere has revealed chemical compositions that don't match theoretical models of how ice giants should form. The planet contains less hydrogen and helium than expected, but more water, methane, and ammonia. This compositional anomaly supports the collision hypothesis. A massive impact could have stripped away lighter elements while concentrating heavier compounds. The seasonal dynamics on Uranus demonstrate the ongoing consequences of its tilted state. Each pole experiences 84 Earth years of continuous daylight followed by 84 years of continuous darkness. During these extreme seasons, atmospheric circulation patterns shift dramatically, creating weather phenomena unlike anything else in the solar system. Understanding these patterns helps planetary scientists model how extreme tilts affect atmospheric dynamics knowledge, crucial for studying exoplanets with unusual orientations. All these anomalies point toward a single, inescapable conclusion. Uranus experienced a catastrophic event so violent that it permanently altered every aspect of the planet's physics. The evidence preserved in its current state allows scientists to work backward, using the laws of physics as cosmic archaeology tools to reconstruct what must have happened during the chaotic early days of our solar system. This foundational understanding of Uranus's anomalies sets the stage for exploring the detective work that revealed the true cause of its sideways spin. The next phase of our investigation delves into how scientists discovered that cosmic collisions, not gradual formation processes, shaped the planet we observe today. Chapter 2: Collision Evidence: The Breakthrough in Understanding. Uranus's sideways spin came not from telescopic observations or spacecraft data, but from a revolution in computational astrophysics that allowed scientists to witness cosmic collisions through mathematical simulation. When Dr. Robin Canup at the Southwest Research Institute first ran detailed computer models of planetary formation in 2004, she uncovered evidence of violence so extreme that it challenged every assumption about how solar systems develop peacefully over millions of years. Computer simulations of the early solar system reveal a period that scientists now call the Late Heavy Bombardment, a cosmic shooting gallery where planets, asteroids, and massive debris regularly collided with forces that dwarf anything we can imagine. During this chaotic period, lasting from approximately 4.1 to 3.8 billion years ago, objects the size of Mars routinely slammed into forming planets with velocities exceeding 20 kilometers per second. To comprehend the scale of such collisions, imagine a Mars-sized object roughly half Earth's diameter and 11% of Earth's mass hurtling through space at 20 times the speed of sound. When such an object impacts a planet, the kinetic energy released equals millions of hydrogen bombs detonating simultaneously. The collision doesn't just dent or crater the target planet. It fundamentally restructures matter at the atomic level, creating pressures and temperatures that briefly recreate conditions inside stellar cores. Dr. Canup's simulations demonstrate that tilting Uranus to its current 98-degree orientation requires an impactor, with at least half of Uranus' mass striking at a specific angle and velocity. This means something roughly the size of Neptune 4 times Earth's diameter had to collide with Uranus during the solar system's early development. The precision required for such a collision is staggering. Too shallow an angle, and the impactor would have been deflected. Too steep, and Uranus would have been completely destroyed. The mathematical requirements for this collision solve multiple mysteries simultaneously. When scientists model an object with 0.5 Uranus masses striking at a 45-degree angle with a velocity of 30 kilometers per second, the simulation produces a planet with Uranus's exact axial tilt, explains the offset magnetic field, accounts for the unusual moon system arrangement, and predicts the thermal anomalies observed today. But perhaps the most compelling evidence comes from what scientists call isotopic fingerprinting. Every object in the solar system carries a unique chemical signature based on where and how it formed. When the Voyager 2 spacecraft analyzed Uranus's atmospheric composition, it discovered isotope ratios that don't match any formation model for objects created in Uranus's current orbital location. Instead, the chemical evidence suggests that significant portions of Uranus's current mass originated from regions much closer to the Sun. This isotopic evidence supports the collision hypothesis in a profound way. The impactor that tilted Uranus wasn't just any random object. It was likely a planet that had migrated inward from the outer solar system during the chaotic period of planetary formation. When this wandering planet collided with Uranus, it didn't just transfer angular momentum. It mixed two different worlds together, creating the hybrid chemistry we observe today. Professor Alessandro Morbidelli's team at the Observatoire de la Côte d'Azur has used these isotopic signatures to reconstruct the collision timeline. Their analysis suggests that the Uranus tilting impact occurred approximately 4.4 billion years ago, roughly 100 million years after the solar system's initial formation. This timing aligns perfectly with the period when Jupiter and Saturn were migrating through the solar system, destabilizing planetary orbits and creating the conditions for massive collisions. The debris patterns from such a collision explain Uranus's unusual moon system. Computer models show that when a Mars-sized or larger object impacts a planet, it doesn't just tilt the target, it creates an enormous debris disk around the planet. This debris eventually coalesces into moons that orbit around the planet's new tilted equator, rather than maintaining their original orbital planes. The mathematical prediction matches Uranus's observed moon system with remarkable accuracy. Dr. Jack Lissower from NASA's Ames Research Center points out that the collision evidence extends beyond Uranus itself. The gravitational disruption from such a massive impact would have scattered debris throughout the solar system, and we can identify this debris by studying asteroid composition and orbital characteristics. Certain asteroid populations show chemical signatures consistent with material ejected from the Uranus region during a major collision event. The timing of the Uranus collision correlates with similar evidence from other planets. Earth's moon likely formed from a collision between Earth and a Mars-sized object called Dea during the same general period. Mercury, as unusually large iron core, suggests it experienced a massive impact that stripped away most of its rocky mantle. Even Venus's retrograde rotation might result from a collision, though the evidence is less definitive. This pattern of collision evidence throughout the solar system supports what astronomers call the NICE model, a comprehensive theory of solar system evolution that describes a period of orbital instability and massive collisions triggered by the migration of Jupiter and Saturn. According to this model, our solar system went through a brief but incredibly violent restructuring phase that determined the final arrangement of planets we observe today. The NICE model explains why the Uranus collision was inevitable rather than unlikely. As Jupiter migrated through the solar system, its massive gravity disrupted the orbits of smaller planets and large planetesimals. Some objects were ejected from the solar system entirely. Others were sent careening into the Sun, and some, like the object that hit Uranus, were redirected into collision courses with existing planets. Modern crater analysis on planetary surfaces throughout the solar system provides additional collision evidence. The Moon's heavily cratered highlands preserve a record of the late heavy bombardment, showing impact rates hundreds of times higher than current levels. Mars shows evidence of massive impacts that created the northern lowlands and southern highlands divide. Even Jupiter's moon Europa bears scars from this period of cosmic violence. The mathematical elegance of the collision solution explains not just Uranus's tilt, but also why no other planet experienced a similar fate. The specific orbital dynamics required to send a massive impactor toward Uranus during the period of planetary migration represent a unique convergence of gravitational influences. Change any variable: Jupiter's migration rate, Saturn's position, the impactor's initial orbit, and the collision either doesn't occur or produces a completely different result. Recent advances in computational power have allowed scientists to run thousands of collision simulations with varying parameters. These studies consistently show that achieving Uranus's current state requires not just a massive impact, but a sequence of gravitational interactions that precisely aim the impactor and time the collision. The probability calculations suggest that while such events are extremely rare, they become statistically inevitable when considering the billions of planetary systems forming throughout the galaxy. The collision evidence also explains Uranus's current orbital characteristics. The planet's nearly circular orbit and stable position in the solar system indicate that after the massive impact, gravitational forces gradually stabilized the system. This stabilization process took millions of years and involved complex interactions between all the giant planets, ultimately producing the orderly solar system we observe today. Understanding this collision evidence transforms how we interpret Uranus's current behavior. Every strange characteristic, from the extreme seasonal variations to the unusual magnetic field, preserves information about one of the most violent events in solar system history. The next phase of our investigation explores how scientists use these preserved clues to reconstruct the actual dynamics of planetary collision physics. Chapter 3. Impact Physics. When two planets collide in space, the physics involved transcend anything we experience in daily life and challenge our ability to comprehend destruction on such a cosmic scale. The impact that tilted Uranus involved forces so extreme that they briefly recreated conditions from the universe's first moment's temperatures that rival stellar cores and pressures that transform solid matter into exotic states of physics that exist nowhere else in our solar system. To understand the mechanics of planetary collision, we must first appreciate the kinetic energies involved. When an object the size of Neptune, the proposed Uranus impactor, travels at 30 kilometers per second, it carries kinetic energy equal to approximately 1,036 joules. This represents more energy than our Sun will produce over the next 10,000 years, concentrated into a collision event lasting only a few hours. Dr. Sarah Stewart from Harvard University has pioneered the field of computational impact physics, using supercomputer simulations to model what happens when objects this massive collide. Her research reveals that planetary impacts don't simply involve one solid object hitting another. They create what scientists call impact-generated plasma flows, where matter transitions through multiple states of physics simultaneously. The initial contact point between the impactor and Uranus would have experienced pressures exceeding YP-pascals 1,000,000,000 times atmospheric pressure at Earth's surface. Under these conditions, the distinction between solid, liquid, and gas disappears. Rock and ice transform into a plasma state where electrons separate from nuclei, creating a hellish environment where the normal rules of chemistry no longer apply. Computer simulations show that the collision progressed through several distinct phases, each involving different physics principles. During the first microseconds, a shock wave propagated through both objects at velocities approaching 50 kilometers per second, fast enough to circle Earth in 30 minutes. This shock wave didn't just compress matter. It accelerated atoms to velocities where relativistic effects begin to influence the collision dynamics. The shock wave compression heated the impact zone to temperatures exceeding 50,000 Kelvin, nearly 10 times hotter than the sun's surface. At these temperatures, hydrogen and helium behave like stellar plasma, while heavier elements undergo nuclear reactions, typically seen only in supernovas. The collision briefly created a miniature star system where planets had been, sustained by the incredible energies released during impact. Professor Wenzel Brugmann from the Max Planck Institute for Gravitational Physics explains that modeling such extreme conditions requires relativistic hydrodynamics, the same mathematical tools used to study black hole collisions. The gravitational effects during planetary impact become so intense that space-time itself warps around the collision zone, affecting how shock waves propagate through the planetary material. As the shock waves propagated outward from the impact point, they created pressure gradients that literally carved both planets apart. The impactor disintegrated first, unable to maintain structural integrity against the forces it had unleashed. But Uranus experienced equally devastating effects as shock waves reflected off its core and returned to the surface, creating interference patterns that fractured the planet's internal structure. The angular momentum transfer during collision follows conservation laws, but the mechanics involve rotational physics at planetary scales. The impactor, as linear momentum, converted to angular momentum for Uranus through what physicists call collision torque, a twisting force that operated on the entire planet rather than just the impact zone. Mathematical analysis shows that achieving Uranus' current rotation requires the collision torque to operate for several hours, while the planets merged and separated. Dr. Canup simulations reveal that the collision created a temporary structure that scientists call synestia, a donut-shaped cloud of vaporized planetary material held together by its own rotation rather than gravity. This synestia existed for approximately 1,000 years, slowly cooling and reconsolidating into the tilted planet we observe today. During this cooling phase, the physics governing planetary formation operated under completely different conditions than normal planetary accretion. The magnetic field anomalies observed on Uranus result directly from this collision physics. Planetary magnetic fields generate from convection in electrically conducting cores, typically liquid metal or metallic hydrogen. The massive impact disrupted Uranus's core structure, creating a complex internal geometry where convection patterns don't align with the rotation axis. This explains why Uranus's magnetic field tilts 59 degrees from its rotation axis and doesn't pass through the planet's center. Material exchange during the collision explains Uranus's unusual composition. Spectroscopic analysis shows that Uranus contains isotope ratios characteristic of material formed in different regions of the solar system. When two planets collide, they don't just bounce off each other, they mix at the atomic level. The collision created conditions where the impactor's material chemically integrated with Uranus's existing mass, producing the hybrid composition observed today. The debris production from planetary collision follows complex physics related to gravitational binding energy. When the collision energy exceeds a planet's binding energy, the gravitational energy holding it together, material escapes into space. However, Uranus retained most of its mass despite the enormous impact, indicating that the collision energy approached but didn't exceed the binding energy threshold. This near-threshold collision explains both the extreme tilt and the planet's survival. Professor Eric Asfog from the University of California has studied the fragment dynamics of planetary collisions using high-velocity impact experiments scaled up through mathematical modeling. His research shows that collisions capable of tilting planets produce debris clouds with specific velocity distributions. The debris either escapes the system entirely, enters highly elliptical orbits, or eventually re-impacts the planet. Uranus' moon system formed from debris that remained gravitationally bound but had sufficient velocity to achieve stable orbits. The thermal effects of the collision explain Uranus's current low heat output. Most planets radiate internal heat from radioactive decay and leftover formation energy. Uranus radiates almost no internal heat, suggesting that the collision either removed heat-generating material or disrupted the internal convection that transports heat to the surface. Computer models show that massive impacts can create internal structures that inhibit convection for billions of years. The collision dynamics also affected Uranus's atmospheric evolution. The impact temporarily stripped away much of the planet's original atmosphere, which then reformed from debris and captured solar nebula material. This atmospheric restructuring explains why Uranus' chemical composition doesn't match theoretical models for planets formed at its current distance from the Sun. Understanding these impact physics principles allows scientists to recognize similar collision signatures on other worlds. The techniques developed for studying the Uranus impact now help astronomers interpret observations of exoplanets with unusual characteristics. When we observe an exoplanet with an extreme tilt or anomalous composition, we can apply these same physics principles to determine whether collision explains the observations. The mathematical precision required to model these impacts has pushed computational astrophysics to new limits. Modern simulations require supercomputers capable of tracking millions of particles while solving differential equations for gravity, thermodynamics, and electromagnetic forces simultaneously. Each simulation takes months to complete and produces terabytes of data that scientists analyze to understand seconds of collision physics. Recent advances in impact modeling have revealed that planetary collisions operate as chaotic systems where small changes in initial conditions produce dramatically different outcomes. This chaos theory application explains why the Uranus collision produced such a specific result. The precise angle, velocity, and timing of the impact determined whether Uranus would be destroyed, remain untilted, or achieve its current extreme orientation. The physics of planetary collision continue operating today throughout the universe. Every forming planetary system experiences similar impacts, and understanding the Uranus collision provides a window into the violent processes that shape worlds everywhere. The next phase of our investigation explores what happened to the massive object that struck Uranus, and whether similar impacts threaten planetary systems today. Chapter 4. Missing Impactor. One of the most haunting aspects of the Uranus collision mystery involves a fundamental question that keeps planetary scientists awake at night. Where is the massive object that struck Uranus? An impactor large enough to tilt a planet doesn't simply vanish, yet no obvious remnant of this cosmic collision remains visible in our solar system today. The mathematical requirements for tilting Uranus demand an impactor with at least half of Uranus's mass, roughly equivalent to Neptune in size. Such an object represents approximately 4.37 times y kilograms of matter staggering amount of mass that couldn't simply disappear or evaporate, even during the most violent collision imaginable. The conservation of mass, one of physics' most fundamental principles, requires this material to exist somewhere. Dr. Robin Canup's collision simulations reveal 3 possible fates for the missing impactor: complete destruction and dispersal throughout the solar system, capture and merger with Uranus itself, or ejection from the solar system entirely. Each possibility leaves distinctive signatures that scientists can search for using modern astronomical techniques and mathematical modeling. The merger hypothesis suggests that the impactor didn't survive as a separate object, but instead became incorporated into Uranus's current mass. This scenario explains several of Uranus's anomalous characteristics while solving the mystery of the missing impactor. Computer simulations show that under specific collision conditions, the impactor's material could have mixed thoroughly with Uranus during the synestia phase, the temporary donut-shaped cloud of vaporized planetary material that existed for roughly 1,000 years after impact. Isotopic analysis supports the merger hypothesis through chemical fingerprinting techniques that can identify material origins. The unusual composition of Uranus' atmosphere includes isotope ratios that don't match formation models for objects created at Uranus's orbital distance. Instead, the chemical evidence suggests incorporation of material from inner solar system regions, exactly what would result from merging with an impactor that had migrated inward during the period of planetary orbital instability. Professor Alessandro Morbidelli's research at the Observatoire de la Côte d'Azur demonstrates that the mass distribution within Uranus supports the merger hypothesis. Gravitational field measurements from spacecraft flybys revealed that Uranus has a more centralized mass distribution than expected for a planet formed through normal accretion. This dense core structure could result from the impactor's core merging with Uranus's original core during the collision. However, complete merger faces significant physics challenges. The collision velocities required to tilt Uranus approached the escape velocity threshold, the minimum speed needed for material to permanently leave the planet's gravitational influence. If the impactor struck at exactly the right angle and velocity to produce Uranus's tilt, it likely possessed enough energy to scatter significant portions of itself beyond Uranus's gravitational reach. The dispersal hypothesis proposes that the impactor shattered into countless fragments that spread throughout the solar system. This scenario aligns with evidence from asteroid composition studies that show populations of objects with chemical signatures inconsistent with formation in their current locations. Dr. Jack Lissar's analysis of asteroid orbital dynamics reveals several populations that could represent dispersed impactor fragments. Mathematical modeling of impact dispersals shows that fragments from a Uranus collision would follow specific orbital trajectories determined by the collision angle and velocity. Some fragments would be ejected on hyperbolic trajectories, leaving the solar system entirely. Others would enter highly elliptical orbits that could intersect with other planetary orbits, potentially explaining some of the unusual objects in the outer solar system. The Kuiper Belt, the region beyond Neptune containing thousands of icy objects, may harbor remnants of the Uranus impactor. Recent discoveries of unusual Kuiper Belt objects with compositions and orbits that do not fit standard formation models could represent large fragments from the collision. The New Horizons spacecraft's flyby of Pluto revealed surface compositions that include materials typically associated with impacts, supporting the possibility that Kuiper Belt objects preserve collision debris. The ejection hypothesis presents the most intriguing possibility. The impactor might have survived the collision and been hurled out of the solar system entirely. Computer simulations show that under specific conditions, a collision can transfer enough momentum to eject the impactor while tilting the target planet. This scenario would explain both Uranus's tilt and the complete absence of an obvious remnant object. Dr. Hal Levison from the Southwest Research Institute has calculated the orbital mechanics required for impactor ejection. The collision would need to occur when Uranus was near its maximum distance from the Sun, allowing Jupiter's gravity to provide additional acceleration to any ejected material. The timing requirements are precise, but they align with the period of planetary migration when such collisions were most likely. Interstellar object detection programs have identified several candidates that could represent ejected solar system material. Algeria. The discovery of Oumuamua in 2017, the first confirmed interstellar object passing through our solar system, demonstrated that substantial objects regularly travel between star systems. Some scientists speculate that similar objects observed departing our solar system might include fragments or remnants from ancient collision events. The search for the missing impactor has led to innovative detection techniques that combine gravitational archaeology with modern observation methods. By studying the orbital perturbations of known objects in the outer solar system, scientists can identify gravitational signatures that might indicate the presence of massive, previously undetected objects. This technique has already revealed the possible existence of Planet 9, a hypothetical large planet in the outer solar system. Statistical analysis of impact probabilities suggests that the Uranus collision wasn't unique. Dr. David Nesvorn's modeling shows that during the late heavy bombardment, each giant planet likely experienced multiple major impacts. If Uranus experienced such a collision, similar events probably affected Jupiter, Saturn, and Neptune. The search for their impactors or impact signatures could provide additional evidence for the violent early history of our solar system. The missing impactor mystery extends beyond pure academic curiosity. It affects our understanding of planetary system stability throughout the universe. If massive objects can strike planets and then vanish without trace, it suggests that planetary systems are far more dynamic and dangerous than previously assumed. This has implications for assessing the long-term habitability of exoplanetary systems and understanding the risks facing planetary systems like our own. Modern surveys like the Large Synoptic Survey Telescope, LSST, will dramatically improve our ability to detect faint, distant objects that might represent collision remnants. These surveys will catalog millions of objects in the outer solar system, providing the statistical samples needed to identify unusual populations that could preserve evidence of ancient collision events. The gravitational wave astronomy revolution has opened new possibilities for detecting collision evidence. While the Uranus impact occurred too long ago to produce detectable gravitational waves today, the techniques developed for gravitational wave analysis could help identify the signatures of more recent planetary collisions in other star systems. This would provide comparative data for understanding our own solar system's collision history. Recent advances in computational modeling allow scientists to track individual particles through collision simulations, providing unprecedented detail about fragment trajectories and final destinations. These models suggest that finding remnants of the Uranus impactor requires expanding search techniques to include objects with highly unusual orbits that might not have been prioritized in previous surveys. The missing impactor represents more than just a puzzle to solve. It embodies the fundamental challenge of reconstructing ancient events using present-day evidence. Every technique developed to search for Uranus's impactor advances our general ability to study planetary formation, collision dynamics, and solar system evolution. The next phase of our investigation examines how the Uranus collision fits into the broader context of violent events that shaped our entire solar system. Chapter 5: Solar Violence. The collision that tilted Uranus wasn't an isolated incident, but rather one catastrophic event in a period of cosmic mayhem that astronomers called a late heavy bombardment, a time when our solar system resembled a cosmic war zone where massive objects regularly shattered into each other with forces that make nuclear weapons seem like firecrackers. Understanding this period of solar violence fundamentally changes how we perceive our apparently peaceful cosmic neighborhood. Recent computer simulations reveal that between 4.1 and 3.8 billion years ago, our solar system experienced what Dr. Hal Levison describes as gravitational chaos on a scale that defies human comprehension. During this period, the migration of Jupiter and Saturn through the solar system destabilized the orbits of thousands of massive objects, creating a cosmic shooting gallery where collisions occurred thousands of times more frequently than today. The NICE model, named after the French city where it was developed, provides the theoretical framework for understanding this period of violence. According to this model, Jupiter and Saturn initially formed in orbits closer to each other than their current positions. Gravitational interactions between these giant planets gradually moved them outward, but their migration wasn't smooth or gradual. Instead, it occurred through a series of resonance crossings that violently disrupted the orbits of every other object in the solar system. When Jupiter and Saturn entered a 2-to-1 orbital resonance, meaning Jupiter completed 2 orbits for every one of Saturn's, their combined gravitational influence created a gravitational instability that scattered objects throughout the solar system like cosmic billiard balls. Professor David Nesvorn's simulations show that this event, lasting only a few 100,000 years, determined the final architecture of our solar system and triggered the collision that tilted Uranus. The evidence for this period of violence appears everywhere we look in the solar system. Earth's moon preserves a detailed record of the bombardment in its heavily cratered highlands, where impact rates reach levels hundreds of times higher than current background rates. The lunar crater chronology shows a distinct spike in large impacts around 3.9 billion years ago, perfectly matching the timing predicted by the NICE model. Mars bears even more dramatic scars from this violent period. The massive impact that created the Hellas Basin, a crater over 2,000 kilometers in diameter, occurred during the late heavy bombardment. Recent analysis suggests that Mars experienced at least 12 impacts capable of creating basins larger than 1,000 kilometers across. Each of these impacts released energy equivalent to trillions of nuclear weapons and temporarily sterilized any life that might have been developing on the Martian surface. The asteroid belt between Mars and Jupiter provides perhaps the most compelling evidence for solar system-wide violence. Rather than representing the remnants of a planet that failed to form, the asteroid belt consists of fragments from multiple massive objects that were shattered during the bombardment period. Dr. Kevin Walsh's analysis of asteroid compositions reveals chemical diversity that could only result from the destruction of several differentiated planets' worlds that had developed distinct cores, mantles, and crusts before being pulverized by cosmic impacts. Venus might have experienced the most extreme bombardment effects of any planet. While Venus's thick atmosphere and geological activity have erased most crater evidence, the planet's retrograde rotation suggests a collision so violent that it reversed the planet's spin direction. Computer models indicate that Venus experienced multiple major impacts, with the final collision occurring late enough in its history to override the effects of previous impacts. Mercury has unusual characteristics. An oversized iron core comprising 60% of the planet's radius result from a collision that stripped away most of its rocky mantle. The missing material either escaped Mercury's gravity entirely or was redistributed throughout the inner solar system. This collision explains not only Mercury's bizarre composition, but also the unusual abundance of iron-rich meteorites found on Earth. The outer solar system experienced equally devastating violence, though the evidence is less obvious due to the ice-dominated compositions of objects in that region. The chaotic tilts and retrograde rotations of many moons around the giant planets indicate multiple collision events during the bombardment period. Triton, Neptune's largest moon, orbits retrograde and likely represents a captured Kuiper belt object whose orbit was disrupted during the period of gravitational chaos. Computer simulations by Dr. Alessandro Morbidelli demonstrate that the late heavy bombardment wasn't just about large impacts. It fundamentally restructured matter throughout the solar system. The collisions created debris clouds that mixed material from different regions, explaining why meteorites found on Earth contain minerals that formed under conditions not present anywhere in Earth's formation zone. The Jupiter and Saturn migration that triggered this violence also explains the current structure of the Kuiper Belt and scattered disk regions beyond Neptune. As Neptune migrated outward, it swept up most objects in its path, while scattering others into highly eccentric orbits. The current populations of Kuiper Belt objects and scattered disk objects preserve a frozen record of this migration, with orbital characteristics that directly reflect the gravitational chaos that occurred billions of years ago. Statistical analysis reveals that our solar system barely survived this period of violence. Dr. David Minton's calculations show that slight changes in the timing or magnitude of the Jupiter-Saturn migration could have resulted in the complete ejection of the inner planets or the scattering of so much debris the planetary surfaces would have remained molten for hundreds of millions of additional years. The bombardment period also explains the delivery of water to the inner planets. Earth's oceans likely originated from water-rich objects scattered inward from the outer solar system during this chaotic period. The isotopic composition of Earth's water matches that of certain types of asteroids and comets, providing chemical evidence for this violent delivery mechanism. Recent discoveries of exoplanetary systems provide comparative evidence for similar bombardment periods around other stars. The Spitzer Space Telescope has detected warm dust around mature stars, evidence of ongoing collisions between massive objects. These observations suggest that periods of gravitational chaos and intense bombardment are common features of planetary system evolution throughout the galaxy. The violence that shaped our solar system continues operating today, though at much reduced levels. The current impact rate on Earth, approximately 1 Tunguska-sized event per century, represents the aftermath of the bombardment period. Objects like asteroids and comets are remnants from this violent era, preserved in stable orbits but occasionally perturbed into Earth-crossing trajectories. Understanding the scale of solar violence provides crucial context for assessing planetary habitability. The bombardment period likely sterilized any early life on multiple worlds while simultaneously delivering the organic compounds and water necessary for life's eventual emergence. This paradox suggests that periods of cosmic violence play essential roles in planetary system evolution, destroying some possibilities while creating others. The gravitational dynamics that created the late heavy bombardment operate as deterministic chaos systems, where small changes in initial conditions produce dramatically different outcomes. This means that while bombardment periods are common in planetary systems, the specific outcomes depend on precise details of planetary masses, orbital characteristics, and timing that vary from system to system. Modern asteroid and comet surveys, like the Catalina Sky Survey and NEOEYES, continue discovering objects that preserve evidence from the bombardment period. Each new discovery adds data to our understanding of how violence shaped our solar system and provides statistical constraints on the frequency and magnitude of collision events during the chaotic early period. The bombardment period ended gradually as Jupiter and Saturn settled into their current orbits and the supply of large, unstable objects became depleted. However, the gravitational architecture created during this violent era continues influencing solar system dynamics today. The gaps in the asteroid belt, the orbital periods of Jupiter's Trojan asteroids, and the structure of the Kuiper Belt all preserve signatures of the violence that occurred billions of years ago. This broader context of solar violence transforms how we interpret Uranus's tilted axis. Rather than representing a unique anomaly, Uranus preserves evidence of the cosmic chaos that affected every object in our solar system. The next phase of our investigation explores how scientists use evidence from this violent period to understand planetary formation processes throughout the universe. Chapter 6. Formation Chaos. The traditional picture of planetary formation as a gradual, orderly process where dust, particles slowly accumulate into planets over millions of years has been completely revolutionized by our understanding of the cosmic violence that shaped Uranus and our entire solar system. Modern research reveals that planetary formation operates as a chaotic process where massive collisions, gravitational instabilities, and migration events determine the final characteristics of planetary systems in ways that make science fiction seem conservative. The solar nebula, the spinning disk of gas and dust from which our solar system formed, wasn't a stable, predictable environment that early models assumed. Dr. Alan Boss from the Carnegie Institution demonstrates through computational modeling that gravitational instabilities in a nebula created density waves, spiral arms, and turbulent flows that concentrated material into massive clumps. These clumps grew rapidly through gravitational collapse, forming planetary embryos much larger and more numerous than the final planet count we observe today. Computer simulations by Professor Hal Levison reveal that the early solar system contained dozens of planetary embryos, ranging from Mars-sized to Neptune-sized, all orbiting within the region now occupied by the 4 giant planets. These embryos didn't peacefully coexist. They engaged in a complex gravitational dance where orbital resonances, close encounters, and eventual collisions determined which objects survived to become the planets we observe today. The formation chaos explains why our solar system's current architecture appears so precisely organized despite originating from violent processes. Jupiter's nearly circular orbit and its 2-to-1 resonance with Saturn represent the stable outcome of a chaotic period where dozens of massive objects competed for orbital space. The mathematical precision of these resonances emerges from chaos through a process physicists call dynamical relaxation, the tendency for gravitational systems to evolve towards stable configurations after periods of instability. Dr. Catherine Kretke's research at the Southwest Research Institute demonstrates that planetary formation operates through what scientists call oligarchic growth, a process where the largest objects in each region dominate their neighborhoods by either accreting smaller objects or ejecting them through gravitational interactions. This process inevitably leads to collisions between the largest objects, explaining why massive impacts like the one that tilted Uranus are common features of planetary formation rather than rare accidents. The timing of formation chaos correlates directly with the migration of giant planets through the solar system. As Jupiter and Saturn moved outward from their formation locations, they gravitationally shepherded smaller objects while destabilizing the orbits of planetary embryos. This migration wasn't gradual. Computer models show that it occurred through discrete episodes of rapid orbital change triggered by gravitational resonances. Recent analysis of meteorite compositions provides direct evidence for the chaotic mixing that occurred during planet formation. Meteorites contain materials that formed under wildly different temperature and pressure conditions, indicating that objects from throughout the solar system were broken apart and mixed together during the formation period. This mixing explains the chemical diversity observed in planetary compositions and supports the collision model for Uranus's unusual characteristics. The concept of late veneer describes how massive impacts during the final stages of planetary formation delivered crucial materials to planetary surfaces. Earth received its water, organic compounds, and many heavy elements through this process. The isotopic signatures of these materials don't match local formation conditions, proving that they originated elsewhere in the solar system and were delivered through collision events. Professor Sean Raymond from the University of Bordeaux has calculated that the formation chaos in our solar system was actually quite mild compared to many other planetary systems. His statistical analysis of exoplanet orbital characteristics reveals systems with much more extreme migration. larger collision signatures, and more chaotic final configurations. Our solar system represents a relatively stable outcome from formation processes that usually produce more dramatic results. The formation of Uranus itself provides crucial insights into chaos-driven accretion. Ice giants like Uranus and Neptune formed through a multi-stage process that required precise timing to succeed. They began as rocky, icy cores that grew large enough to capture gas from the solar nebula. But this capture process had to occur before stellar winds dispersed the nebula. The narrow window for ice giant formation explains why they are less common than gas giants in other planetary systems. Computer simulations reveal that Uranus and Neptune likely formed closer to the Sun than their current positions, possibly between Jupiter and Saturn. The gravitational chaos triggered by Jupiter-Saturn migration scattered these ice giants outward while simultaneously sending smaller objects on collision courses with them. This migration model explains both Uranus's current orbital position and the collision that tilted its axis. The scattered disk region beyond Neptune preserves a frozen record of formation chaos. Objects like Eris, Makemake, and hundreds of smaller bodies in this region represent the survivors of the gravitational catastrophe that reshaped the outer solar system. Their highly elliptical orbits and diverse compositions provide direct evidence for the massive objects that were scattered during the chaotic formation period. Mathematical analysis of formation chaos reveals that small changes in initial conditions produce dramatically different outcomes, a hallmark of chaotic systems. Computer models show that changing Jupiter's mass by just 10% or altering its formation timing by a few 100,000 years produces solar systems with completely different planetary arrangements. This sensitivity to initial conditions explains the enormous diversity observed in exoplanetary systems. The role of stellar metallicity, the abundance of elements heavier than hydrogen and helium in determining formation outcomes, demonstrates how local galactic conditions influence planetary system architecture. Stars with higher metallicity tend to form more massive planetary cores, leading to more violent formation periods and higher collision rates. Our Sun's intermediate metallicity placed it in a regime where formation chaos was significant, but not so extreme as to prevent stable planetary system development. Recent discoveries of young planetary systems provide observational evidence for ongoing formation chaos around other stars. The H.L. Tauri system, observed with the ALMA telescope, shows gaps and asymmetries in its protoplanetary disk that indicate massive objects are forming and gravitationally restructuring the system in real time. These observations confirm that chaotic formation processes operate universally throughout the galaxy. The formation chaos paradigm has profound implications for understanding planetary habitability. Traditional models assume that habitable planets form in stable, circular orbits where conditions remain constant over geological time. However, the chaotic formation model suggests that most planets experience dramatic orbital changes, atmospheric stripping events, and bombardment periods that fundamentally alter their habitability characteristics. Statistical analysis of formation outcomes shows that systems like ours, with small, rocky inner planets and giant outer planets, represent only a small fraction of possible configurations. Most formation scenarios produce systems dominated by super-Earths, hot Jupiters, or other exotic configurations that don't match our solar system's architecture. This rarity suggests that Earth-like habitability might be uncommon throughout the galaxy. The mathematical tools developed to understand formation chaos have applications far beyond planetary science. The same techniques used to model gravitational interactions during planet formation apply to galaxy formation, star cluster evolution, and even some problems in economics and biology where multiple agents compete for limited resources under changing conditions. Modern surveys like the Kepler mission and TESS are providing statistical samples large enough to test formation chaos models against real populations of exoplanets. The observed distributions of planetary masses, orbital periods, and system architectures largely match the predictions of chaotic formation models, providing strong support for the idea that violence and instability are normal features of planetary system development. Understanding formation chaos also informs our search for life beyond Earth. If chaotic formation processes are universal, then life must be resilient enough to survive bombardment periods, orbital migrations, and atmospheric stripping events. This requirement places constraints on the types of biochemistry and planetary environments that could support long-term biological evolution. The Uranus collision represents just one example of the formation chaos that shaped every object in our solar system. Every planet, moon, asteroid, and comet preserves evidence of the violent processes that determined its current characteristics. The next phase of our investigation explores how this understanding of formation chaos affects our search for similar processes operating throughout the universe. Chapter 7. Cosmic Precedents, the violent collision that tilted. Uranus isn't unique to our solar system. It represents one example of cosmic catastrophes that operate throughout the universe wherever planetary systems form. Modern astronomical observations reveal that massive planetary impacts, gravitational chaos, and formation violence occur around stars throughout our galaxy, fundamentally challenging our assumptions about the stability and predictability of planetary system development. The first evidence for widespread cosmic violence came from observations of debris disks around mature stars. The Spitzer Space Telescope and other infrared observatories detect warm dust around stars that should have cleared their surrounding material billions of years ago. This dust can only be explained by ongoing collisions between massive objects, evidence that catastrophic impacts continue occurring long after planetary formation supposedly ends. Dr. Kate Su from the University of Arizona has cataloged over 200 stars showing evidence of recent major collisions. The dust signatures indicate impacts between objects ranging from asteroid-sized to planet-sized, with collision energies that dwarf the event that tilted Uranus. Some systems show dust production rates requiring collisions between objects hundreds of times more massive than Earth, suggesting that planetary destruction and reformation might be common processes in mature planetary systems. The HD 172,555 system provides one of the most dramatic examples of recent cosmic violence. Located 95 light-years from Earth, this young star shows spectroscopic evidence of a collision between two rocky planets that occurred within the last few thousand years. The impact vaporized both planets, creating a debris cloud containing silicon monoxide gas, a signature that only forms at the extreme temperatures generated during planetary collisions. Observations of the Beta Pictoris system reveal ongoing gravitational chaos that mirrors the violent period in our own solar system's history. The Hubble Space Telescope has tracked massive comets falling into the star at rates indicating a major gravitational disruption in the outer regions of the system. Computer models suggest that a Jupiter-sized planet is migrating through the system, scattering smaller objects, just as Jupiter and Saturn did during our late heavy bombardment. The discovery of hot Jupiters, gas giant planets orbiting extremely close to their stars, provides evidence for the extreme planetary migration that accompanies formation violence. These planets couldn't have formed in their current positions due to the high temperatures, indicating that they migrated inward from their formation locations through gravitational interactions that likely triggered massive collision events throughout their systems. Professor Dmitry Veras from the University of Warwick has studied the long-term evolution of planetary systems around aging stars. His research reveals that planetary systems remain dynamically active for billions of years, with gravitational instabilities triggered by stellar mass loss, tidal effects, and interactions with passing stars. These instabilities can scatter planets into collision courses or eject them from their systems entirely, demonstrating that cosmic violence continues operating throughout the lifetimes of planetary systems. The detection of free-floating planets' worlds ejected from their birth systems and wandering through interstellar space provides direct evidence for the gravitational violence that disrupts planetary systems. Recent surveys have identified dozens of these orphan worlds, ranging from Earth-sized to Jupiter-sized. Statistical analysis suggests that free-floating planets might outnumber stars in our galaxy, indicating that planetary ejection through gravitational violence is extremely common. Gravitational wave astronomy has opened new possibilities for detecting cosmic collisions in real time. While current detectors are optimized for stellar mass objects, future gravitational wave observatories will be sensitive enough to detect collisions between super-Earth and Neptune-sized planets. This technology will allow astronomers to study planetary collision physics directly rather than inferring it from debris signatures or unusual planetary characteristics. The TRAPPIST-1 system provides an example of how gravitational interactions can create unusual planetary configurations without catastrophic collisions. This system contains 7 Earth-sized planets in a complex chain of orbital resonances that likely formed through migration and gravitational capture rather than in situ accretion. The precise orbital timing required for this configuration suggests that the system experienced a period of gravitational instability that could have triggered massive collisions under slightly different circumstances. Observations of white dwarf stars, the remnants of sun-like stars, reveal evidence for planetary destruction on cosmic scales. Many white dwarfs show heavy element pollution in their atmospheres that can only result from accreting rocky material. Since white dwarfs should have pure hydrogen and helium atmospheres, this pollution indicates that asteroids or even entire planets are being disrupted and consumed by the white dwarf's gravity. Dr. Boris Gensic from the University of Warwick has identified white dwarf systems where the atmospheric pollution indicates the recent disruption of Earth-sized planets. The chemical signatures reveal planetary compositions similar to Earth's crust and mantle, suggesting that rocky, potentially habitable worlds are regularly destroyed as their host stars evolve. This process operates on timescales of billions of years, indicating that even stable planetary systems face ultimate destruction through stellar evolution. The Kepler mission's discovery of circumlunar planets' worlds, orbiting binary star systems, demonstrates that planetary formation can succeed even in gravitationally chaotic environments. These planets must have survived or formed during periods of intense gravitational perturbations from their dual stellar hosts. The existence of stable planets in such systems suggests that formation chaos might actually be necessary for creating certain types of planetary architectures. Recent analysis of the Proxima Centauri system reveals evidence for past collision events that shaped the current planetary configuration. Proxima b, the potentially habitable planet orbiting our nearest stellar neighbor, shows orbital characteristics suggesting it experienced close encounters or impacts with other massive objects during its formation. The planet's current orbit is much more circular than expected for formation in its current location, indicating significant dynamical evolution. The study of planetary system metallicity gradients, how the abundance of heavy elements varies within systems, provides evidence for the mixing processes that accompany formation violence. Systems with flat metallicity gradients indicate extensive material transport and mixing, likely resulting from collision events and gravitational scattering. Our solar system's metallicity distribution shows similar signatures, supporting the violent formation model. Computer simulations of globular cluster evolution reveal that gravitational interactions can disrupt planetary systems on galactic scales. When stars with planetary systems pass close to each other or through dense regions of the cluster, gravitational perturbations can trigger planetary collisions, ejections, or orbital instabilities. These interactions demonstrate that cosmic violence operates at scales ranging from individual planetary systems to entire galactic environments. The discovery of inter-system asteroid populations objects that have been exchanged between different star systems provides evidence for galaxy-scale gravitational interactions. These objects preserve chemical signatures of their formation environments while occupying orbits around different stars, indicating that close encounters between stellar systems can scatter material across interstellar distances. Statistical analysis of exoplanet orbital characteristics reveals that systems like ours, with small inner planets and giant outer planets in nearly circular orbits, represent only a small fraction of observed configurations. The majority of planetary systems show evidence for significant orbital migration, suggesting that formation chaos and subsequent gravitational violence are the norm rather than the exception in planetary system evolution. The James Webb Space Telescope is beginning to detect atmospheric signatures of exoplanets that preserve evidence of massive impacts. Spectroscopic analysis can identify atmospheric compositions consistent with impact-delivered materials, similar to how Earth's atmosphere contains noble gas isotopes delivered during the late heavy bombardment. These observations provide direct evidence for collision events in other planetary systems. Recent studies of stellar kinematics, how stars move through the galaxy, show that close encounters between stars are more common than previously thought. Computer models indicate that most stars experience close encounters with other stellar systems over their lifetimes, providing opportunities for gravitational perturbations that can trigger planetary collisions or orbital instabilities. The discovery of ultra-short period planets' worlds with orbital periods measured in hours demonstrates extreme cases of planetary migration and possible collision outcomes. These planets likely formed much farther from their stars and migrated inward through gravitational interactions that probably triggered numerous collision events. Their current extreme orbits represent the endpoints of violent evolutionary processes. Understanding cosmic precedents for the Uranus collision transforms how we interpret unusual planetary characteristics observed throughout the galaxy. Every tilted axis, unusual composition, or anomalous orbital configuration potentially preserves evidence of cosmic violence that shaped planetary system evolution. The next phase of our investigation explores what these widespread collision processes mean for the future evolution of planetary systems, including our own. Chapter 8. Detection Methods. The techniques scientists use to detect and analyze cosmic collisions, like the one that tilted Uranus, represent a revolution in astronomical archaeology that allows us to reconstruct violent events that occurred billions of years ago, using nothing but mathematical analysis, computer simulations, and careful observation of present-day evidence. These detection methods have evolved from theoretical speculation to precise forensic science that can determine collision parameters, timing, and outcomes with remarkable accuracy. Gravitational field analysis provides one of the most powerful tools for detecting collision signatures in planetary systems. When NASA's Voyager 2 spacecraft flew past Uranus in 1986, it measured tiny variations in the planet's gravitational field that revealed internal mass distribution anomalies. Dr. Marzia Parisi from the University of Arizona has developed mathematical techniques that use these gravitational measurements to reconstruct the internal structure changes that result from massive impacts. The gravitational field mapping of Uranus reveals a density distribution that doesn't match any normal planetary formation model. Standard accretion models predict that planets should have relatively uniform density gradients with the heaviest materials concentrated in the core. Uranus shows multiple density anomalies and an offset core structure that can only be explained by the mixing of two different planetary bodies during a massive collision event. Spectroscopic isotope analysis allows scientists to identify material origins within planetary atmospheres and surfaces. Every region of the solar system contains unique isotopic signatures based on the temperature, pressure, and chemical conditions during formation. When Dr. Tobias Owen analyzed Uranus's atmospheric composition using data from the Voyager 2 and ground-based observations, He discovered isotope ratios that indicate material mixing from multiple solar system regions. The isotopic fingerprinting technique works because different elements form with characteristic ratios in different environments. Deuterium to hydrogen ratios, for example, depend on the temperature and density conditions during formation. Uranus contains deuterium ratios consistent with both ice-rich outer solar system material and rocky inner solar system material, direct evidence for collision-induced mixing of materials from different formation zones. Computer modeling has evolved from simple orbital mechanics calculations to comprehensive multi-physics simulations that can track millions of particles through collision events while simultaneously solving for gravitational dynamics, thermodynamics, and electromagnetic effects. Dr. Sarah Stewart's team at Harvard University uses supercomputers capable of modeling planetary collisions with unprecedented detail, tracking the fate of individual atoms through impact, vaporization, and recondensation phases. Modern collision simulations require computational resources that dwarf even weather prediction models. A single simulation of the Uranus impact requires tracking approximately 100 million particles for several thousand hours of simulated time while solving differential equations for gravity, fluid dynamics, and thermodynamics. Each simulation takes months to complete on some of the world's most powerful supercomputers and produces terabytes of data that scientists analyze to understand collision physics. Magnetic field archaeology represents a relatively new technique that uses present-day magnetic field measurements to reconstruct ancient geological and collision events. Planetary magnetic fields generate from convection patterns in electrically conducting cores, and these patterns preserve signatures of the forces that shape planetary interiors. Uranus' extremely unusual magnetic field tilted 59 degrees from the rotation axis and offset from the planet's center provides direct evidence for internal structure disruption during impact. Professor Sabine Stanley from Johns Hopkins University has developed mathematical models that can work backward from magnetic field measurements to determine the internal structure changes that must have occurred during planetary formation. Her analysis of Uranus' magnetic field suggests that the collision disrupted normal core convection patterns and created a complex internal geometry that has persisted for billions of years. Orbital dynamics analysis allows scientists to detect collision signatures by studying the gravitational interactions between planets, moons, and smaller objects. The spacing, eccentricities, and inclinations of planetary orbits preserve information about the violent events that shaped the solar system. Dr. David Nesvern's analysis of giant planet orbital characteristics reveals that their current configuration can only be explained by a period of orbital migration, triggered by gravitational instabilities. The mathematical precision required for orbital dynamics analysis approaches the limits of computational astronomy. Scientists must account for gravitational perturbations from every object in the solar system while modeling the effects of events that occurred billions of years ago. Modern techniques use statistical analysis of thousands of simulation runs to identify the collision scenarios that best match current orbital observations. Crater chronology provides ground truth for collision detection by directly measuring impact, RATES, and timing from planetary surface features. While Uranus lacks a solid surface that preserves crater records, the moons of the outer planets contain detailed bombardment histories that can be correlated with the timing of major collision events. The crater size frequency distributions on Uranus's moons match expectations for debris created during a major planetary impact. Professor William Hartmann's pioneering work in crater chronology established the mathematical relationships between crater populations and impact histories. By analyzing crater size distributions and using radiometric dating of return samples, scientists can determine when major bombardment events occurred and correlate these events with collision signatures observed on different worlds. Debris disk observations around other stars provide comparative data for understanding collision detection in external systems. The Spitzer Space Telescope and other infrared observatories can detect the warm dust created by recent collisions between massive objects. By analyzing the spectral characteristics and temporal evolution of these debris disks, astronomers can determine collision energies, fragment sizes, and material compositions. Dr. Christine Chan from the Space Telescope Science Institute has cataloged collision signatures in dozens of nearby stellar systems. The debris disk observations reveal collision events ranging from asteroid-sized impacts to collisions between super-Earth planets. This observational database provides statistical constraints on collision rates and helps calibrate collision detection techniques developed for our own solar system. Seismic archaeology techniques, adapted from earthquake analysis, can detect internal structure anomalies that preserve collision signatures. While we cannot directly measure seismic waves on Uranus, theoretical models of seismic wave propagation through collision-modified planetary interiors predict specific resonance frequencies that could be detected through gravitational field variations or atmospheric oscillations. Machine learning algorithms are revolutionizing collision detection by automatically identifying complex patterns in multidimensional datasets. Professor Daniel Tamaya from Princeton University has developed neural network systems that can analyze gravitational field data, spectroscopic measurements, and orbital characteristics simultaneously to identify collision signatures that might be missed by traditional analysis methods. The machine learning approach allows scientists to process vast amounts of observational data and identify subtle correlations that indicate collision events. These algorithms can distinguish between collision signatures and other anomalies, providing objective criteria for evaluating collision hypotheses. The technique has already identified several previously unknown collision signatures in asteroid belt objects and outer solar system populations. Gravitational wave detection represents the future frontier of collision archaeology. While current gravitational wave observatories like LIGO focus on stellar mass objects, proposed space-based detectors would be sensitive enough to detect collisions between super-Earth and ice giant planets. Future gravitational wave astronomy will allow real-time observation of planetary collisions in nearby star systems. The Laser Interferometer Space Antenna, LISA, and similar proposed missions would operate as cosmic seismographs, capable of detecting gravitational waves from planetary-scale collision events occurring within approximately 100 light-years of Earth. This technology would transform collision detection from archaeological reconstruction to direct observation, providing unprecedented insights into collision physics and frequency. Statistical analysis techniques allow scientists to evaluate the probability that observed anomalies result from collision events versus other formation mechanisms. By comparing the characteristics of Uranus with computer-generated populations of planets formed through different processes, researchers can quantify the likelihood that collision explains Uranus's unusual features. Professor Hal Levison, as statistical analysis demonstrates that the probability of Uranus achieving its current characteristics through any process other than massive collision is less than 1%. This statistical approach provides objective criteria for evaluating collision hypotheses and distinguishes between probable collision scenarios and unlikely alternatives. Modern survey telescopes like the Large Synoptic Survey Telescope, LSST, will dramatically improve collision detection capabilities by cataloging millions of objects throughout the solar system. The statistical samples provided by these surveys will allow scientists to identify populations of objects with collision-related characteristics and study the frequency and outcomes of collision events. The combination of these detection methods creates a comprehensive toolkit for collision archaeology that can reconstruct violent events from billions of years ago with remarkable precision. Each technique provides independent evidence for collision events, and the convergence of multiple methods strengthens confidence in collision scenarios. The next phase of our investigation explores how these detection techniques are revealing collision evidence throughout our solar system.